Right, ladies and gentlemen, let's continue with chapter 4 in the textbook of Cengel and Ghajar. Chapter 4 is on transient heat conduction. We've completed with the previous lecture the lump system analysis, which was paragraph 4.1, and today we're going to do paragraph 4.2. Paragraph 4.1 on a lump system approach or analysis. The important thing there is to remember that we have derived an extremely easy equation that can be solved, but that equation has many limitations. It cannot give the temperatures at different positions in a body. The temperature, the answer is the temperature everywhere. And for most bodies, that is not relevant. For most bodies, that's not relevant. There's a small percentage of bodies where it is relevant. And those are typically bodies where the dimensions is very, very small and the thermal conductivity is very high. And that is being prescribed by the Biot number. The Biot number gives us the ratio of the resistance, the conduction resistance divided by the convection resistance. The convection is on the surface and it wants to go in, but how quickly it can go in is being determined by the resistance of the body itself. And we have found, or it was mentioned, that if the Biot number is smaller than 0.1, then normally you will get a good approximation. Something else that was very important there is in the calculation of the Biot number, the characteristic length, to determine that it can be calculated by using the volume divided by the surface area. Now remember, this approach is just valid for lump systems. You're going to see as we start working through the material now that you cannot do that in general. Right, so let's continue with paragraph 4.2. Paragraph 4.2 is on the transient heat conduction. Transient heat conduction in large plane walls, LPW, it's just large plane walls, long cylinders, okay, and spheres. So those three bodies we are going to consider in paragraph 4.2. They are simple in terms of geometry and analytical solutions are available for them. So a large plane wall, let's draw this large plane wall here. This is the large plane wall. Okay. And with large, we mean that the surface area here and there is negligible in comparison with the rest of the area. Okay. So that is why we say that is a long plane wall, LPW, long plane wall. And in terms of the coordinate system X, take note, and that is very important, the dimension here is equal to L, and that distance there is equal to 2L. This is just going to be used in the analytical solution, and it makes the analytical solution easier to solve. Okay, then schematically, the long cylinder, here's the long cylinder. Now I do not have enough room on the board, otherwise I would have made it much, much longer. So again, this is not infinite, but extremely large or long in comparison with the radius. So the heat transfer on this surface and the heat transfer on that surface is negligible in comparison with the rest. And again, in terms of the coordinate system, it will be solved as a function of r, and this distance from the center line to the outside surface is equal to r0, and the result is that that distance there is 2 times r0, like that. The third type of body is a sphere. And in a sphere, again, that is R, and that is equal to R0. and the diameter of the sphere is 2 times R0. Okay, in terms of this is a cylinder, CYL, and this is the sphere, SPH. In this chapter, or in this paragraph, we are going to get analytical solutions for these three types of geometries. Simple geometries, just to start with. Now, coming back again to the lump system approach that we've looked at yesterday, and now in paragraph 4.2 onwards, the approach that we're going to use. Let's just look again what is the difference between the two. In the lump system approach, which was considered specifically in paragraph 4.1, if we want a solution of the temperature in different positions, let's suppose we are interested in the temperature at that point there, at that point there, and that point there, 1, 2, and 3, and let's choose 3 arbitrary points also, in this one and in that one also, 1, 2, 3. Okay. For the lump system approach, all those temperatures, the temperatures as function of time, temperature as function of time, for all those points 1, 2, and 3 would give the same solution. So it would not say that this temperature is 100 and that one is 90 and that is 80. It would be 100 everywhere. With the approach that we're going to follow now, temperature as a function of time, here we're going to have different time temperature variations, something like that, and that is what we are interested in this paragraph, and that is what we are not going to solve in this paragraph. Okay. So from chapter 2, now we're going to look at the mathematics a little bit. From chapter 2, you have already derived the heat conduction equation in 3 dimensions, and it looks like this. There's partial d2t dz squared plus E gen divided by k is equal to 1 divided by alpha dt dt. The one t, capital T, is for temperature, and the other t is for time. And this alpha is the thermal diffusivity. If you can't remember, it's the thermal diffusivity. And it is equal to K divided by rho Cp. So that is the general equation in 3 dimensions. If we look at these types of problems, which are the simplest types available, then we will see that the heat transfer rate is in 1 dimension only. As we said, there are no temperatures or heat transfer coming from here, from the top and the bottom. Everything is in 1 dimension only. It would therefore mean that if you've got the temperature, remember this is very long, if you've got the temperature at the center at this point, then it would also be the temperature at the center there, and it would also be the temperature there. This temperature would be the same as there, there, and there, and there, and the same there. So therefore the heat transfer rate is in 1 dimension only. So for that reason, we are not going to consider those 2 terms, and that is then the general heat conduction equation, which is now valid for this problem. So the differential equation, first one there on the slide, there it is. You've got it there. And let's just look at typically the boundary conditions. Let's suppose that is the temperature Ti through the plane wall or the cylinder, and then suddenly the temperature is increased to T infinite on the outside. Let's suppose this temperature is 0 and that temperature is 100. What would we expect with the temperatures? What will happen at the temperatures? Well, firstly, we can expect that the temperatures on the side is going to increase, isn't it? Because they are the closest. So we're going to have a temperature distribution typically like that. And because of symmetry, if it's 100 degrees on this side and 100 degrees on this side, then that temperature and that temperature is going to be the same. Okay? So my curve is not that good, but it should be symmetrical, and that gradient there should be equal to 0. And then a few seconds later, it will do something like that. Okay? Do you agree? And then later on, this temperature in the center is going to start decreasing. You're going to start getting something like that. Until a very, very long time, then the temperature right through the body would be T infinite, that of the outside temperature. The important thing here is the boundary condition that we have here. And the boundary condition says that this gradient is equal to 0. That's the first boundary condition that we need to solve this problem. Then the second boundary condition is to say that the conduction heat transfer into the body is equal to the convection heat transfer into the body. Now that boundary condition says minus K multiplied by the area partial dt dx is equal to the heat transfer coefficient multiplied by the area multiplied by the temperature minus T infinite. Okay, and the areas, of course, would cancel out. And then we've got an initial condition. Any partial differential equation needs an initial condition to start with, and that initial condition is very easy, and that is that when T is equal to 0, then the temperature throughout the body is equal to Ti. Now, to solve this partial differential equation, what has been done is to write it in a non-dimensionalized format. So we've got capital X, which is equal to small x divided by L. What is small x? Small x is just this distance. Okay. So there, capital X would be equal to 0, and there it would be equal to 1. Okay, because x is equal to L. So it means that the distance is always non-dimensionalized. It will always be between 0 and 1. Then we also non-dimensionalize the temperature, which is equal to the temperature, which is a function of x of t minus T infinite divided by Ti minus T infinite. Non-dimensionalized temperature. It would therefore means that if we write it, if this is, okay, here on the outside, we should actually put T infinite there and T infinite there, I forgot, the heat transfer coefficient 8, H, and it's the same with all the other bodies. And initially, the temperature is equal to Ti. T is equal to Ti, and T is equal to Ti. Okay. So that non-dimensionalized temperature tells us that if that temperature is suddenly 100 and that was equal to 0, okay, and you go and calculate it, then you will always see that depending on if the temperature is originally at Ti or later at equal to T infinite, the non-dimensionalized temperature will always be between 0 and 1. The Biot number we've done with the previous lecture is equal to the heat transfer coefficient multiplied by L divided by the thermal conductivity. K is the Biot number, and the Biot number is the dimensionless heat transfer coefficient. HTC is heat transfer coefficient. I'm going to use it a lot in this module because it's a very important thing that we're going to use a lot. The dimensionless heat transfer coefficient, the Biot number. Then, what is also defined is tau, which is alpha t divided by L squared, is equal to the Fourier number, and that is the dimensionless time. And again, this time will then always varies between 0 and 1. No, sorry, it wouldn't vary between 0 and 1. It can be larger than 1. Okay. So, why are we doing all this stuff? Where are we going to? Well, what was done by non-dimensionalizing all these numbers, the Biot number, the Fourier number, etc., is that the number of independent variables has been reduced from 8 to 3. Because the non-dimensionalized temperature now is a function of x, the Biot number, and tau. Okay. And these 8 variables that we had previously was x, it was L, it was time, it was K, alpha, H, Ti, and T infinite. The temperature is dependent on all 8 of those variables. By non-dimensionalizing it, the temperature is now a function of x, Biot, and tau, only 3 variables. And this equation can be solved by either the Laplace, by using the Laplace equation, or the separation of variables. Okay. And in this paragraph, this last method is used, the separation of variables. Now, we are not going to go through the whole derivation because it's not a mathematics module that you're doing now, but you've done it already in mathematics. Let me just show you some of the very important steps. Okay, so this is that's the initial condition, there's the non-dimensionalized temperature, and this is where the separation of variable methods now start. It's been written like that, and the result is a dimensionless differential equation. The boundary conditions can also be written in a dimensionless format, as well as the initial conditions. Again, there's all our non-dimensionalized variables, and going through that up to there, and here's the derivation, separation of variables, sorry, there it starts, and here we start generating the solution. Okay, so all those equations are in your textbook, and you're going to use many of them a lot. But let me just show to you some of the most important ones. So one of them is lambda n, tan lambda n, is equal to the Biot number, which means there's an infinite number of roots because it's a cost function. Okay, so there's an infinite number of roots, and this equation is called the characteristic equation of the eigenfunction. The roots are the characteristic values or the eigenvalues, and it has an infinite number of solutions. So that is part of the solution. Then the next thing that's part of the solution is the non-dimensionalized temperature, theta, which can be written from the sum of n equal 1 to infinite of an e to the minus lambda n squared tau multiplied by cos lambda n x. Okay. And then, what is this an there? Here we can see where we can get lambda n. You can put it into the equation, but you need an, and the solution for an looks like this. It is equal to 4 times the sinus of lambda n divided by 2 times lambda n plus the sine of 2 times lambda n. Now, this is a little bit, quite some work to go and calculate it, especially if you don't have a computer or a computer to do it with. A shortcut that can be used is that you can typically get the results in a table, but I'll show you just now. But the important thing is that the solutions are being given in table 4.1. Now take a good look. There's the geometries, plane wall, the cylinder and the sphere. There's the solution as a function of theta, and there's the roots. And there's an error there in the textbook, okay, or on my PowerPoint. Okay. Yeah, that is the answer, so that is what it should be. So this short derivation that is being shown in your textbook in a little bit more detail is specifically for the long plane wall. You can go and do it then also for the cylinder and the sphere. There's the solutions and there's the roots. Two things which is very important if you take a look at it. Firstly, there is a J01 value in there, as well as a J1. There's J0 and J1. Who of you can remember what that is? It is the solution of the Bessel functions. Okay? I'm going to explain it to you just now. But before we do that, take note of the fine print in the table, and I'm going to mention this a lot. There's some fine print in it because it tells you how you must calculate the non-dimensionalized temperature, the Biot number, and the Fourier number. Okay. And it says J0 and J1 are the Bessel functions of the first kind whose values are given in table 4.3. Now before we get to table 4.3, what is important is to realize that this is the exact solution that has been given there. I've also written here. But it is not convenient to work with. It's a lot of work because you have to go and calculate. You have to go and start with n equal 1, do all the calculations, then you need to do it for n equal to 2, n equal to 3, etc. Fortunately, these values for n equal to 2, 3, and 4, etc. is getting less and less and less. So the question that's always asked, well, when can I make the approximation and when can I use n equal to 1 only? And the answer for that is if tau is larger than 0.2. So if tau is larger than 0.2, then the error will be smaller than 2%. So if the time is given to us, we can calculate tau and you can check it. In other cases, it is not given, and that is maybe what is asked. Then you make the assumption that that is the case. You do the calculation, you calculate tau then, and then you check if it is smaller or larger than 0.2. There are, of course, very special cases. And the special cases is the case, if we come back to this sketch here, where we would like to have the temperature in the center. So if it is in the center, that non-dimensionalized temperature would be called theta 0. It's indicated in the center. there it is the same. That would be theta 0, and that would be theta 0. If we look at this solution, for lambda, it is lambda moment x, and x is equal to x divided by L. So in the center x, which is equal to x divided by L, is equal to 0. Do you agree? Okay. And that term, the cos, if that is equal to 0, it would be the cos of 0, and that would be equal to 1. Okay. Therefore means that if we are interested in the solution at the center, that part of the equation would disappear. It makes it easier for us in terms of the calculations that we need to do. So, if we now want to look at typically, if we can look at this table specifically, let's look at the case where the Biot number is equal to 5. And x is equal to 1. What does x equal to 1 mean? X equal 1, x is capital X is equal to x divided by L. X equal 1 means x should be equal to L. So that would be the case for on the surface. Okay. So this is the solution for the temperature on the surface, and the time T is equal to 0.2. If we go and put it into these equations now and solve it, then you would see that if n is equal to 1, then lambda n is equal to 1.3138. I'm going to show you just now where you're going to get it. An is equal to 1.2402, and the non-dimensionalized temperature would be equal to 0.22321. Okay? You see that? Okay. Now for the case where n is equal to 2, there is lambda n, there is An, and now we see the non-dimensionalized temperature as 0.00835. We can see it is small, and that it will only, if you add this value with that value, it will only have an influence on that second digit. You agree? Okay. If you do it for n equal to 3, then the non-dimensionalized temperature is equal to 0.00001. Okay. You see? And then the same for n equal to 4, then it wouldn't even, there wouldn't even be a number into the first 5 or 6 digits. Where do we get these values from? Well, we get it from a table in your textbook, table 4.2. You're going to use that table quite a lot, as well as in table 4.3. Coming back to the previous problem, take note, there is the results for a plane wall, and it gives the value for lambda and for A. There's for a cylinder, and there is for a sphere. Here we can see the answers is a function of the Biot number. And the problem that we've looked at just now was for a Biot number of 5. Okay? For a Biot number of 5, lambda 1 is equal to 1.3138, and A1 is equal to 1.2403. Okay? So that is where those values come from. Let me just go back. Again, there it is. Lambda 1 and An is 1. If we then put it into that equation, it is very easy to calculate theta. Okay? Then there's table 4.3. And table 4.3 shows eta, and then it shows J0 in eta and J1 in eta. Now, students who didn't work through these problems would think that it's very easy to jump from there to there, and in principle it is, but the complications, the calculations is more complicated. And many students then for the first time thought that they know what is eta, and now suddenly eta appears, and then they say, where do I get eta? How do I calculate eta? Okay. Now eta is just the value that we want for the Bessel function. So for example, in one of the equations, what is required is the 0th order Bessel function multiplied by lambda n r divided by r0. Okay? So if you calculate this and it is equal to 0.3, then it just means eta is equal to 0.3. So it means that you just go down this table, you look where eta is 0.3, and then you can get the Bessel function there, J0, and you can get the Bessel function J1. Okay? So it is not a strange new variable that appeared. What we can also do is in terms of the temperatures, as I've mentioned, that is the temperature at the center. Because the cost terms disappeared, it can be written as a very simple equation, A1 e to the minus lambda 1 squared multiplied by tau. There were the values for n equal 1 only, so that would be when we make the assumption that tau is larger than 0.2. And then let's jump to what is called the Heisler charts. The Heisler charts has been developed by Heisler in 1947, and that was the time before computers, so it was a lot of work to do all these calculations. And what he did is he presented the results in a graphical form so that it's easier and quicker, but of course it is not that accurate. How it works is, in principle, you will see that on every page there's 3 graphs. Okay. The first one is for theta 0. What does theta 0 mean? It is the temperature at the center. Every one of the sketches also here at the right bottom have a sketch. And the sketch typically for a large plane wall is given there as well as the coordinate system so that you don't make a mistake. So all the information is in front of you. So here it gives the non-dimensionalized temperature, and it writes it as the temperature 0, temperature in the center, minus T infinite divided by Ti minus T 0, like that. And this is the non-dimensionalized time, which is equal to alpha T divided by L squared. And here's the results in terms of 1 divided by the Biot number is equal to K divided by HL. Okay. Right. So there are always 3 variables. You need 2 to solve the other one. Suppose the time is given. The time, so we want the solution after 1 minute. Then you can calculate this. You'll obviously have the properties of the material, so you've got alpha, and L is the dimensions of the large plane wall, the thickness, or the half thickness. So you can calculate that. Do you agree? Okay, so let's suppose that is the value there. Again, if you've got the properties of the body, the K value, its dimension, and the heat transfer coefficient, you can calculate the Biot number. So you can get the relevant line there. Let's suppose it is that line there. So then it is very easy. You would go up there, and there you will find the solution. Okay. T infinite is the temperature on the outside. Ti is the initial temperature. T0, the temperature at the center. So you can get it from there. The next graph is a follow-up on the first graph. And this follow-up graph gives the results as theta divided by theta 0. And on this scale, it has 1 divided by the Biot number, which is equal to k divided by HL. And here we've got the solution of x divided by L. So theta would now be maybe the temperature at that point there. We want the temperature halfway between the center and the outside surface. Again, if we now look at this, we can identify from the x value. So in this case, it will be x divided by L is equal to 0.5. You can select the graph. The Biot number, you can get there, and then you get that value. Okay. Theta divided by theta 0. This means that if you want the temperature inside the body, you always first have to calculate theta 0. Okay. First get the temperature at the center. With that known, you can put it in there, then you can calculate theta at any other position in the body. Okay, so that is the other graph. So that was the first one was theta 0. That's the second one, theta divided by theta 0. Look at the sketch there. It's very easy. And then the last one is the heat transfer chart, from which you can get the heat transfer rate at any point in time. And this figure looks like this. It gives theta, the heat transfer rate divided by theta max. And something like that. Here we've got the Biot number. The Biot square multiplied by tau. And here we've got the Biot number. And again, it is very easy to do the calculation. Okay, now when do you use the equations and when do you use the Heisler charts? Most obviously, the equations is much more accurate, but what I like to do is I do it with the equations and then I check it on the graph to see if you can get approximately the same value. Sometimes the lines on the graph are so close to each other that it is very difficult to make a judgment in terms of where it is. So that is why you'll see that the graphs are not that accurate. The last thing that we need to speak about is the Fourier number tau. What does the Fourier number means? The Fourier number indicates the heat conducted divided by the heat that has been stored inside the body. So let's suppose we've got a body like this. And that is the heat transfer rate going into the body. Okay. And going to draw it like that. Okay. So this is the heat transfer rate which is conducted through the body. It is going through. And this is the heat transfer that is being stored on the inside. Okay. It's like a tank of water with holes in it. The holes would represent the conduction heat transfer, where the heat transfer goes out or the water goes out. This, although the arrow is showing in this direction, maybe I should have rather draw it like that. Much bigger body. Okay. And this heat is absorbed everywhere. It doesn't go out on this surface. So let's suppose that surface is insulated. Everything is being stored inside the body. So that is what the Fourier number represents. Any questions? This is not a lecture that I have enjoyed. It is lots of detail. But with the next lecture, we're going to do a few examples, and then it will become clearer to you. Okay? But just, it is important that it's not necessary for you to remember the whole derivation, to understand it, and or to be able to do it, but you need to go through it so that you can have a good understanding of what is happening on the inside, so that you can use the equations correctly. And I will concentrate on that in the next lecture. Thank you, ladies and gentlemen.